Alright, so,
Bet you haven't heard this one.
hey, Patty. So probability. A lot of stuff we're doing and talking about today is stuff you've probably talked about in Algebra 1 and probably in Geometry a little bit, because I think you've hit this both years. This is our second to last unit for the year, and the last unit's a really short one, so this is really our last big unit.
Yes.
It is a little bit tougher once we get into the probability stuff towards the end. Stuff at the beginning should be pretty simple, but towards the end it's going to get a little more difficult. Today talking about determining experimental and theoretical situations, complements of events, and probability of two events or compound events. First things first, so probability. The probability of something happening, right, that top blank on top, is a number of ways it could happen divided by the total number of outcomes. A lot of times people leave things in fractions, which is awesome. Sometimes they'll do probabilities in percentages, sometimes in decimals, all sorts of things. Probabilities can range from 0 to 1 if we're talking about fractions or decimals, and from 0 to 100 if we're talking about percents. Right? Obviously, if it's 1 and it's a fraction, that means that there's a guaranteed chance it'll happen. 100% is a guaranteed chance it'll happen. And 0 in either fractions or percents means that it will never happen. Right? So, like flipping a coin is a 50-50 chance.
What?
1 in 6 chance of rolling a die. If it gets to 0, like I said, it'll never happen. 1, it'll have to happen. 1 is the same as like 100% chance of it happening.
Can you go scroll up real quick?
Scroll up real quick. Sure, Quentin. Like I said, a lot of the stuff we're going to talk about here at the start is going to be a lot of review from Algebra 1 geometry. You good? Go on, sorry. Who's at the door? Sure. Can I have your review? Sweet. Do you want to do it in here, or otherwise there's people taking it in that other room?
I'll go to the other room.
Okay. You know where the other room is?
No.
Here's the test. If you need a round, it'll tell you what to round to on there. And then the room they're taking it in.
Another word I use so fast.
You like it.
You don't want it. You don't want it.
Alright.
You don't want
Alright, so definitions of probability. Probability does not tell us exactly what will happen. Just give us a guide. So an experiment or trial is an action where the result is uncertain. Right? So an experiment or trial is basically when we talk about anything, we're talking about probability. So an example might be flipping a coin. That's an experiment, right? That's a trial. So one example, flipping a coin, rolling a die. Anything like that could be an example. Right? Those are experiments, those are trials. Flipping a coin. I should finish writing that. Could do rolling a die, could do picking a card, things like that. An outcome is a possible result of that experiment. So, like if I say flipping a coin, if I'm going to stick with this example, what would some outcomes be?
Heads or tails?
Heads or tails. So let's say landing on heads would be our outcome.
Landing on the side.
If we're talking about rolling a die, one of my outcomes could be rolling a 3 or rolling a 5, right? Those are all different outcomes. And then the sample space is all the possible outcomes. So like for this one, flipping a coin, our sample space would be heads and tails. Those are the only two outcomes we get when we flip a coin. Unless you're a magician, you can make it land on its side. If we're talking about rolling a die, what would our sample space be?
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6, right? A normal die has 6 sides with the numbers 1 through 6 in them. So our sample space would be 1, 2, 3, 4, 5, 6. Pretty simple, right? Any questions so far? Alright. Theoretical and experimental probability. Before we talk about it. Does anyone remember the difference between theoretical and experimental? Mason?
Experimental is when you like actually do it, you find the results, and theoretical is like what you should get.
Perfect. That's the exact way I would describe it. Theoretical probability, it uses math to find the results that you should get. It's the probability that it should happen. In theory, it would happen. Right? It's using math. When you say rolling a die, there's a 1 in 6 chance of rolling a 3. Yet if you do the experiment, you might get more than 1 3 in 6 rolls. So theoretical is, in theory, what should happen. Right? Should's that key word there. Experimental probability. Sorry if I'm going too fast, just yell at me. Experimental probability, it's based on data that you collect. It's actually doing the experiment or doing the trials. It's what actually happens, not theoretical, but what you actually did. So if you flip a coin 50 times, you might not get 25 heads and 25 tails. You might get a little different probability based on what you actually got for your data. Right? So experimental is when you actually do it and the probability you get from that. Theoretical is what should happen in theory. Now, with experimental probability, if you do your experiment or your trial millions upon millions upon billions upon billions upon billions of time, it should theoretically spread out to that theoretical probability. It should get really close to having that same set of probability as theoretically it should. Now, if you do it, flip a coin 50 times, the odds that you get 25 and 25 are very slim of heads and tails, right? But if you do it billions of times, you should get really, really close to 50% on each. Does that make sense? Any questions on experimental and theoretical? Did you have enough time to write stuff down?
Yeah.
Okay.
Rough.
All right. Is it? Oh, yeah. All right. Go back. So next thing to talk about is a complement of an event. Does anyone remember what a complement is?
Something nice you said is.
Well, yes, that's true. But spelled differently, the complement, like in your note
It's a
packet.
homonym.
Sure.
Something
I don't know.
It is. Right.
He's right. I'm not an English teacher, but he's right. What does the complement in this text mean? Does anyone remember?
Told you.
So, if
Like,
you want to give an example, you can give an example.
like if the probability of rolling a 3 is 1/6, and then the complement is 5/6.
Exactly, yeah. The complement is the probability that it won't happen. So a complement event, all outcomes that are not the event. So like Mason said, if our normal trial, our normal outcome that we want is rolling a 5, and that probability is 1 out of 6, the complement then will be 5 out of 6. It'll be all the events that wouldn't accomplish our goal. So like if the event is heads, the complement would be tails. When the event is Monday, Wednesday out of a week, the complement would be Tuesday, Thursday, Friday, Saturday, Sunday. If the event is picking a hearts out of a deck of cards, the complement would be spades, clubs, diamonds, and jokers if you have these in there. So any of these examples would work for that. What would be an example? An event and its complement represent the complete set of possible outcomes. So anytime we're talking about an event and its complement, they should add to 1. Right? So the probability of an event happening and the probability of the opposite happening, or the complement, if I add those two probabilities together, it should equal 1. Or if you're dealing with percentages, it should equal 100%. Alright, so it's the opposite of what we want to happen, or the opposite of the outcome. Does that make sense? Any questions on that? Okay, let's keep going then. Complementary events, complement of event, like we said, all outcomes that happen. If we look here, our first example, probability that we get yellow on that spinner is what?
1/4.
1/4. The probability of not yellow, or the complement of yellow, that's what this little squiggly line means. Remember, that's the symbol for complement. So it'd be 3/4. Example, probability of rolling an even number on a die. Well, it'd be 3 out of 6, which is the same as 1/2, right? We would always reduce it. So put in 1/2 would be perfect, right? So make sure you reduce your probabilities. So what's the probability of not an even, or the complement of even? Same thing, 1/2. Right? 3 out of 6 are odd, so it'd be 1/2. All right, a glass jar contains 6 red, 5 green, 8 blue, and 3 yellow marbles. What's the probability to pick a yellow marble?
3/27.
3 out of 2. Where'd you get 22 from, Patrick?
6 plus 5 is 8 plus 3.
6 plus 5 plus 8 plus 3. Right? It's the total number of marbles. So we have 22 total marbles in here. There are 3 yellow marbles, so 3 out of 22 that we pick yellow. So what's the probability that we don't pick a yellow, or that we get the complement of yellow? 19 out of 22. Be the other 19 marbles that are in there. All right? Any questions? Alright, compound events then. Compound event is made up of two or more events that can happen either at the same time or one or the other. Alright, so a compound event, right, just like a compound sentence, you combine two parts of a sentence. A compound event is two or more happenings at once. So there's two different types of compound events. There's independent events and dependent events. The first one we're going to talk about, independent events. Independent events where one event does not affect the other event. So where one event does not affect another event. So an example would be like when you roll a die and you spin a spinner. Or you roll a die and you pick a card out of a deck. Or you flip a coin and you spin a spinner. Right? Things that have no bearing on each other. Right? It doesn't matter what card I pull out of the deck, it's not going to influence what I roll on the die. Those are independent events. Does that make sense? Look at they're all there.
Wait, what would be a dependent event?
We'll talk about that in a second. Okay? Now, when we're dealing with these compound events, independent events, like I said, when the outcome does not affect the second event, what happens is we get the probability of the first event and the second event. That little comma is the same as writing the word and. Alright? So when we deal with probability with compound events, it's going to be a comma. We multiply the probabilities together to find the total probability of them both happening. Right? So the probability that we roll an even number. Well, let's think about that for a second. What's the probability to roll an even number? 1/2. This is actually at the back side. If you flip over your page. 1/2. And spinning it out. Right? That comma is an and, so I'm going to multiply. What's the probability I spin it on? This is labeled 1 through 8. 1/2 again, right? 1, 2, 3, 4 numbers out of 8, so 1/2. So what will the probability be of it, them both happening? 1/4, right? 1/2 times 1/2 is 1/4. Okay. What about picking a jack and flipping tails? Well, what's the probability I pick a jack out of the cards?
4 out of 52.
What?
4 out of 52.
4 out of 52, which is the same as 1/13. Times, what's the probability I flip tails? 1/2. So 1/13
126.
times 1/2 is 1/26. Hey guys, if you're ever confused about like card problems, you really don't understand like what's in a deck of cards or how many of certain things are in there, come ask. Right? We're not trying to trip you up on problems like on a test or on the exam or on reviews or on any homework because you don't know what a deck of cards is. Alright? If you have problems with that, come ask. We'll help you. Alright? Any questions on that? Dependent events then. Well, the outcome of one event does affect the outcome of the second event. So like an example here, Q, of a dependent event, would be choosing a marble at random from a bag containing 3 blue, 5 red, 2 green, and not replacing that marble, and then picking again from there. Right? That's going to change the outcome of that second event.
Yeah.
So they depend on one another. So you do not replace it. What's the total number of marbles we have?
95 to 10.
10. 10 total. Wow, spelling's hard today. 10 total. So the probability of picking a blue
Is
and then a green. So what's the probability of picking a blue, first of all?
3 out of 10.
3 out of 10. Now, notice, it said not replacing. Guys, those little keys in the problems are huge. That changes our whole problem. If we don't replace it, now you want to pick a green then, so we multiply by, what's the probability of picking a green now?
6 out of 9.
6 out of 9. So there's only 9 marbles left, and then we picked one out, and we set it to the side. So 6 out of 9. 6 out of 9. Wait, what? 2 out of 9. Where'd you get 6 from?
No, it's 6. It's 6 over 90 for.
6 over 9. Okay, that makes sense. So 2 out of 9. So there's 2 green out of 9 total. And then, what do you think we should do to 6 over 90?
Reduce.
Reduce it. Reduce it. Reduces to 1/15. So the probability to pick a blue and then a green will be 1/15. Alright, what about picking a red and then another red? Well, first of all, Dom, what's the probability to pick a red out of there first? 5 out of 10 or 1/2. Right? If you want to write 5 out of 10, you get the same exact answer. It's not a huge deal. Well then, Billy, what would be the probability of them picking another red after that? Hey, I'm asking Billy, thank you.
Yeah, that's not your name.
We were talking about something before that.
If I took one red out already, and I set it to the side, what's the probability I pick another red?
4 out of 9.
4 out of 9, right? There's 4 reds left, and there's 9 total. So I get 4 over 18, which reduces to
2 over 9.
2 over 9. Alright, next one, probably picking green and then a yellow. Well, Kuji, what's the probability I pick a green?
2 out of 10 or 1/5.
2 out of 10 or 1/5 times, Noel, what's the probability I pick a yellow?
0.
Noel. What? 0, right? There's no yellows in there, so 0. 0 out of 9, technically, if you want to do it that way. Comes 0 out of 45, which is just 0. It'll never happen because we don't have any yellows. It's impossible. Alright? So independent events do not rely on each other. Dependent events do rely on each other. Okay? Another type of event, what we call mutually exclusive events. Mutually exclusive. So events that cannot occur at the same time are called mutually exclusive. It's like rolling a 2 or a 4. Right? We can roll the die, but we can't roll 2 and 4 at the same time. It's physically impossible. Right? If I roll a die once, can I roll a 2 and a 4 at the same time? No. They're mutually exclusive. They can't happen at the same time. So what happens is when we have an OR there, because it's mutually exclusive, we're going to add the 2 probabilities. Instead of multiplying them, we're going to add the probabilities together. So rolling a 2 would be what probability? 1/6. When you see OR, we're going to add another 1/6 because I know probability of rolling a 4 is 1/6. So I add those together. What do I get when I add 1/6 and 1/6?
1/3.
We get 1/3 because it is
2/6.
2 over 6. Alright, picking a king or a queen. Well, how many kings are in the deck? 4 out of 52. Plus, how many queens are in the deck? 4 out of 52. Now, if you wanted to use 1 over 13 and 1 over 13, that's more than acceptable, it's fine. I get 8 over 52, which reduces to 2 over 13. Alright? What about the next one? Probably picking a diamonds or a heart. Well, how many diamonds are there in the deck?
Go ahead.
13 out of 52. Plus, how many hearts are there in the deck then, you think?
13.
13 out of 52. If you want to use 1/4 and 1/4, you're more than welcome to. So we get 26 over 52, which is the same as 1/2. Does that make sense so far? Do you have any questions so far?
No.
No? Alright, the last one like this. The probability of picking an ace or a club. Someone walk me through it. What do you think? Colton, what did you say?
Yeah, 13 out of 52 plus 13 out of
An ace? There's 13 aces.
Oh, wait, no, there's 4.
There's 4 out of 52.
Plus 4 out of 52. Or a club?
That's 13.
13 clubs plus 13 out of 52.
Okay, hold on though. There's 13 clubs. But, Kuji, what happens?
One of them is an ace, so it would only be 12 out of 50.
One of them is an ace. We can't double count that ace of clubs. We gotta be really careful. Right? We counted the ace of clubs with the 4 aces. So instead of writing 13 out of 52, it's only gonna be 12 out of 52.
That's gonna trip me up.
So we gotta be really careful. Can't double count those cards. So we get 16 over 52, which reduces to what? 4 over 13. Alright, so don't double count those cards. You can't double count that ace of clubs. Alright, one last thing you gotta do. Right, this is super quick. If you see and or a comma, you will multiply the probabilities, right? We talked about that. Those compound probabilities where we saw and or a comma, we're going to multiply. If we see or, we're going to add the probabilities. I'll take it. Thanks. Just enough for us to be done. So, and means multiply, or means add. Any questions? No? Bless you. What we got today?
Tests.
What?
We'll look at tests.
We can.